So this was one interesting study from the same group. This is Paulus's group that did that core 2000 paper, TDCS paper. And you can see there the classic montage, right, with the electrode over M1 and the other one over the front of the head. And what they thought was, well, when we do this, we think half the current doesn't actually enter the brain. Half of it just slips along the scalp, right? Half of it slips along the scalp. The other part into the head, so we're losing half the juice. So why don't we do this? Why don't we take the electrode and move it farther away? And by moving it farther away, our thinking is, right, sort of rule of thumb thinking, that more current should enter the head, and therefore the modulation of M1 should be more efficacious. Sort of like a little rule of thumb. And so this was the idea, that you increase the electrode distance, you move the electrodes farther apart. Because of less scalp shunting, you get more current into the flow. And what they actually found was the opposite. The farther away, the farther apart the electrodes were, right, the less efficacy you got as far as M1 modulation. And to this credit, this group never shies away from publishing backward, unintuitive results, and they went ahead and published it. But we followed up with a modeling study, and this is not, this is actually from a separate paper, but it makes the same idea. So on the bottom case, what you're seeing is the classic M1 SO montage, this time with a little bit smaller pads. And what you're seeing is the same pattern observed earlier. Current is simply flowing between the pads, right? And yes, you hit some of M1. Dylan, is this M1 or is this M1? The left, okay. So it's not like you're not getting M1, but you're certainly not stimulating. You wouldn't call this, just stimulating M1. In this case now, we took a pad, we left this pad, the active pad, where it belongs, but we simulated moving the return pad to the back of the neck. And we did this for another study that Felipe was running. But what we found was this pattern of brain current flow. Now what's happening here is that the current, instead of flowing forward, right, it's flowing sideways, and it's sort of slipping down, right, the temporal side, heading towards the other electrode. And if you look specifically at M1, there's less current in M1, right? I wouldn't say that there's less current going into the head. I wouldn't, you really need to look at the whole picture, right? But if the only thing you cared about was activating M1, right, then this, using a rule of thumb and just moving the electrode farther away may not work. And then you could think, well, maybe then instead of putting the return on the, so to make a long story short, they tried some alternative montages, right, hoping to enhance efficacy. And actually the things that they thought would be less effective were more effective, and the things they thought might be more effective were less effective, but these were their results. And then independently, when I had my engineers run the simulations, they came to the same conclusions, right? Based on targeting M1, they were able to correctly predict which montages should work and which were not. But the rules of thumb were not always right. So models can, yeah.
Just one thing that I mentioned in my lecture, just for knowledge and confusion, because I said the distance and the shunting, that when you have the distance, in this case, you also change the direction of the current. It's not just increasing the distance, because I also showed this, but I gave the example here in the both cephalic electrodes, that if you increase the distance, then it might get less than the model will do it, but then keeping the same direction.
Right, yeah. Right. So there's, and I'm Felipe, what's the best montage for pain?
Okay. I think so far, this study, we're not looking for the best montage, we're looking for if that would work. But the study so far is M1 stimulation. So having M1 supraorbital, the classic montage. But again, not the best, it's the best so far, but not the optimal.
And Felipe is running a 4x1 fibromyalgia study now. Yeah. So, but I don't know how well. Yeah.
We don't know yet the effect sizes. It is significant, the effects, but we don't know the effect sizes if it's better or not. Not yet.
Do you have it over the motor cortex too?
Over the motor cortex.
We frequently have cerebral angiograms along with MR data. So the question is, if we have local blood flow data, should it inform the placement of the electrodes in the
in the sense of which areas you want to target, or in the sense that it will affect current flow?
Both.
I mean, for the first question, I would refer, to the guys who actually do this stuff. The only thing I can say is that it's known that DC current leads to blood vessel dilation. I mean, you put it on your hand and you see it. And so I'm pretty sure that in the brain as well, the stimulation itself will enhance blood flow to any given region in a way that's not polarity specific. So as far as, but the first question, so what we do is we stop at, if you put the montage here or there, this is where the current is going to go. The next question of, well, which montage is better, or based on this additional information, which montage should I use, we cannot answer that question. And we know, we sort of have our limits. So we can, really what we produce is just these pictures. And it's hard to, I hope these pictures help you make that decision, but which regions you want to target are the regions you want to avoid. I think if you look at the existing literature and then look at the models that were run since then, you might think, well, maybe they're seeing an effect not because of the target they were going for. But what's nice about these models is if you do, let's say, have any criteria, so let's say you use any data, functional imaging data, any data to identify a target, you can then use the models to optimize activating that target. And then you'll see,
Once you have your model that has constructed all the different layers parsed out, how long does it take to run the simulation for a given montage?
The amount of time has been dropping a lot. It used to take us a week. Now for some models it takes us a day. It can take an hour. There's a lot, and I'll show you. One of the things we've been trying to do is we're trying to make it take a second. Right, so that when you want to explore a new montage, right, wouldn't it be nice if you can just log into like a website and say, show me this montage, and you get the result. And I'll show you that website, which is something that we're working on. So the answer to the question really depends. Usually on the state-of-the-art side, if you're doing something new, like individualized stroke modeling, it could be a month per head to do something, but it's sort of like the premium stuff, the higher end stuff, it goes slower, and then the stuff that used to take a week a few years ago now takes an hour. So it's decreasing very rapidly. And the computers are getting so much, they never stop getting better and better. It's amazing. Here's another just quick example. This is the classic TDCS montage. This was an article also with Felipe that's coming out on migraine. But our contribution was really just to model current flow, and we looked through certain deeper brain structures, and there's a video here, and this again was not surprising. When you put two pads here, the current is not going to enter, right, the sort of gray matter, disappear, and then sort of reappear in the gray matter somewhere else, right? It's going to flow through everything in between. White matter, and when you put such large electrodes so far apart, it's going to hit a lot of deep structures as well. And in this case, they were interested in this because these particular structures were relevant for pain, right? So this montage was not optimized to hit these structures. In fact, this is like the most standard montage used, but it's hitting all these deeper structures as well. And so, it may affect how you interpret your designs. And really, I think one thing that's interesting is, in the past few years, you look at the clinical literature, people no longer say a nodal stimulation of M1. They'll say a nodal stimulation over M1. That you can say, right? You can say I put my anode over M1. And I think that's a very fair thing to say, right? And I put my cathode over something else. But I think people, definitely have started to shy a little bit away about saying, a nodal stimulation of M1 for exactly these reasons. Just have a few more minutes, so let me see. Oh, they want me to go to Argentina again? So this is an example of a study we did for stroke. So in stroke, you have these regions of the brain that are sort of blown out, and amazingly to me, when I learned about it, they get filled with CSF, and CSF's a real superhighway for current. And so the thinking was, could current flow, use the exact same montage in this person as you would in a healthy person, but could the current flow be completely different? And the same tools are showing you help address it. And this has been published, so you can reference the paper. But to make a long story short, absolutely, this person, you can see the lesion, right? And you can see all that activation on the inside of the lesion. That is because that lesion is almost like a virtual electrode. It's full of CSF, and it's sucking in all the current, and that current is then flowing through and into the brain. So it's hitting, and you can see it sort of flushing into the CSF here, and it's actually hitting this inner structure very intensely. It's actually flowing through, and it's using this other ventricle to get back. And so it's not a trivial pattern, but it's certainly not what you'd see in the healthy head. And this here, by the way, where my cursor is, was the target based on fMRI. And though the subject was a very strong responder, by putting the electrode over, right, the region of interest, they certainly weren't activating as strongly. While, for example, if you use a 4x2 montage, this is the target here again, you can get very targeted activation of that region. So I think with these new montages, it's not just always about being more focal, it's just even just hitting the region that you're interested in and not having the current avoided. And again, this is just a model prediction, but now this is Julius Fredrickson. They're running a prospective trial where every patient gets customized therapy, and we'll see how well that, the proof will be in the pudding. We'll see how well that performs against regular TDCS, which, as you know, works pretty well. This is just another example. This is a patient that was run in a study here. This person had a defect, a blowout, a lesion in their occipital, and they lost some vision, and they were part of a rehab study. And what we simply did was, again, modeled current flow in this particular subject who was responsive to stimulation. This was the montage that was used, right? So just intuitively what they did is they wanted to activate, right, occipital. So they put the anode over occipital, right? And they put the return electrode at the most innocuous place, right, they could maybe think about, or some rules of thumb. But as you know by now, if you've seen any of the images, of course current is going to affect the entire brain region, under and in between, and that's what the model showed. What was curious was that they did fMRI in these subjects before and after rehab, and they were able to examine where there were changes in fMRI signal, and it was a little bit scattered, and the current flow was also scattered, but when we put these into the same sort of space, we were able to show that there was a statistically significant correlation, right, between where the current went and where you had functional changes. And this was a little bit, we sort of knew this would happen in a sense, because you're going to get functional changes in the occipital cortex because you're doing rehab for vision, and we put the electrode over the occipital cortex, you know what I mean? So on a gross level, yeah, of course they're going to correlate, but in this paper, we dug into it a little bit and showed how it would not be so intuitive. So that's really my time. I want to go back to this example. Sometimes it does work out. Sometimes it does work out the way you think, right? I mean, it's not always like you don't even want to look at the model because you're going to get bad news. Sometimes your intuition will be right. This particular example, it worked out just fine, right? Because they put the electrodes all the way across, and they got very nice radial current flow. And there's other things we're working on. I showed you already, right? There's modeling in children. There's modeling in aging adults for different reasons why you might do stimulation in aging adults, where the brain has shrunk. And I don't think we can address whether the aging brain will respond differently to electrical current, but we could definitely say whether 1 milliamp on an elderly head will cause a completely different pattern of current flow. It was mentioned about doing stimulation with people with pre-existing implants. Again, modeling can help with that, as they can with situations where you have skull defects, where you may or may not want to leverage those skull defects to deliver current flow. And that was that paper. Okay, so that's my time, so thank you for your attention.